In this video, we'll talk about some properties of definite integrals. So while it's really hard to find the actual value of a definite integral at this point, we don't have very many techniques to do that. All we have is limits of Riemann sums. The fact they correspond to areas under curves means we have some nice properties we can write about these integrals. The first of these is linearity. So linearity says the following. Basically, if I look at the integral from a to b of f of x plus g of x, this is the area under the combined curve of f plus g. Well, if we think about f plus g as the graph of f and I stack the graph of g on top of it, it makes sense this will be the same area as if I just took the area under the graph of f and then added the area under g. So I can add two functions and take their integral, or I can integrate two functions, add them afterwards, and I'll get the same number from either side of this equation. In addition, if I look at, say, the integral of c times f of x for any number c, this is the same thing as c times the integral of f of x. Why is that? Well, if I look at the graph of f, look at the graph of 2 times f, the graph of 2 times f will have double the area under it because it's just twice as tall. From just the fact that these are areas, we can figure out these two properties hold for integrals as well. It in particular tells us that the integral from a to b of c f of x minus d g of x, I can move the constants and the subtraction out. C integral f of x from a to b minus d integral from a to b of g of x. It all works that way. Another thing we do with definite integrals is to change the order limits of integration. So if I want to look at just the integral from a to b f of x dx, is actually equal to negative the integral from b to a f of x dx. That'd be a strange property at first, but the way you want to think about this is I get to this integral by looking at the limit of Riemann sums, where I'm taking function values at a certain height times some change in x that is my width. Now normally I've got my lengths for my widths going together in the right order, but if I go from b to a instead of a to b, I'm basically changing the sign on this delta x. This delta x, when I shift over here, becomes a negative delta x, and that negative sign gives me this minus sign out front here. The main thing to think about is if I switch the limits of integration, so I put the one on top, one on the bottom, and I swap them, that's going to be a minus sign for my answer. One consequence of this, what does this say about the integral from a to a f of x dx? Well, if I swap the limits, what happens? I will get negative the integral from a to a of f of x dx. Whatever this number is, this number has to equal its own negative. There's only one number that does it, and that's 0. So this fact tells us that if I integrate an integrable function from a to a, if I have 0 width in my interval of integration, I just get 0. Another nice property is I have the additive property of adjacent intervals. So that's the following. If I look at the integral from a up to some c f of x dx, and I add the integral from c up to b f of x dx, this is the same thing as the integral from a up to b f of x dx. While we think about that, let's draw a picture. So if I want to look at the integral from a to c of x dx, that finds this little area in here. This is a to c f of x dx, computes that area. Integral from c to b f of x dx computes this area. And so if I add those two together, I get the full area, which is the integral from a to b f of x dx. So I just kind of piece these areas together, and because I can just stick these areas together and find the total area that way, that gives me a way to work this out. Now c does not have to be between a and b to work this out. If c is outside, I can do the same thing. So say I have a that's here, b over here, and c over here. Then the integral from a to c of f of x gives me the negative of the area inside this part. Then when I do c to b, I will take this area with a positive sign to cancel that out, and then I'll grab this area for the rest of it, which gives me the actual integral I'm looking for, integral a to b f of x dx. So if I have a c on the top and a c on the bottom, I can sort of squish them together and get rid of them and make it one integral at the end. One other nice property is that the comparison theorem, which again comes down to areas. So if f of x is a bigger function than g of x on the interval a to b, then the integral from a to b of f of x is bigger than the integral of g of x. The basic idea being a bigger function contains a bigger area. Which makes sense. If I move the graph function higher, it's going to contain more area under it, and that's what this is telling me here. If I take a bigger function, there's a larger area inside of it. You can also use numbers. So for instance, if, say, f of x is less than 1 on the interval from 1 to 3, then this theorem tells me the integral from 1 to 3 of f of x is less than the integral from 1 to 3 of 1. But this is just a rectangle with area 2. So this is equal to 2, so it tells me the integral is less than 2. Now let's use some of these properties. If we know the integral from 1 to 5 of f of x dx is 8, from 3 to 1 for f of x I get 3, and from 3 to 5 g of x dx I get minus 2, I want to find this integral. Integral from 3 to 5 of 4f of x minus 3g of x. First thing we see is if we knew the integral from 3 to 5 of f of x, we'd be done. Why? Because I know the integral from 3 to 5 for g. I can put that in for this g effectively because I can use linearity to move the constants out. The only thing I'm missing is the value for f, and then I'm good. But how can I get the integral from 3 to 5 f of x dx? Well, that I can get from my additive property for adjacent intervals. I know that the integral from 1 to 5 of f of x equals the integral from 1 to 3 f of x dx plus the integral from 3 to 5. Because I can add these two together, squish them greater the 3's, and get down to 1 to 5. But I am told that this number is 8, and this number is 3, which means this number here has to be 5. Then we get that the integral from 3 to 5 of 4 f of x minus 3 g of x is 4 integral from 3 to 5 f of x using linearity minus 3 integral from 3 to 5 g of x dx. This I know is 5. This from above I know is minus 2. Therefore, I get 20 plus 6, or 26. Those are some properties of definite integrals and how we can use them to solve certain types of problems that we'll see become a lot more useful later on.